Hello and welcome to AP Chemistry, a discussion on photoelectron spectroscopy. Um, the paragraphs you see are in your notes. I'm not going to go over them specifically, but it goes over the process of photoelectron spectroscopy in decent detail. What we need to keep in mind here is the big picture of what's happening. A sample of certain atoms is exposed to some high energy radiation sufficient to strip the electrons off. Okay? And if we know the value of that photon energy, and then we know the resultant kinetic energy of the particle that was ejected from the atoms, we can calculate with a great degree of fidelity the amount of electron, or the amount of energy that was holding those electrons on to the atom. And of course, for any atom of more than hydrogen's energy levels, will have more than one energy of electrons ejected. Okay, and so there's your principle. We know the energy input, we know the energy output, we can subtract to determine the energy that was holding the object on. So this is taking advantage of the photoelectric effect, whereby high energy photons of ultraviolet X-ray radiation are exposed to a sample of matter, and that matter's electrons are ejected, collected and focused into a beam, and then analyzed inside the spectrometer itself in a vacuum. And the resultant beam will be split into the various energies of its contents. So generally what we see is something like this. And we'll see a couple different models in this discussion. But our x-axis is going to be energy in some unit, sometimes electron volts or joules or somewhere in between. But we won't have to worry about what it is. We know that that will be energy on the x-axis and something to quantify the number of electrons of that energy on the y-axis. Sometimes you'll see the highest energy going toward the right. Sometimes the highest energy is here on the left. Your job is to read the data for what it is, to determine what's given to you and in what orientation you'll have to determine. So in the model given to us, we see that we have the highest energy electrons here. So that would be consistent with the 1s orbital electrons. And here we would have the second orbital peak for 2s electron. So we have 1s2, 2s1. Since this peak is twice the height of this peak, there are twice as many electrons of this energy compared to this. So here's neon's photoelectron spectroscopy, and the highest value for our ionization energy is here. And so that would be our 1s peak, and then our 2s peak, and then our 2p peak. The 2p peak is approximately 3 times higher, which is consistent with 6 electrons being in that orbital. And here is an unknown, but we can again look for our highest energy peak here. Notice we have some breaks here and here. Those breaks are designed to allow us to use our brain to say, okay, well, there's no way we're going to fit all those in one page, so we're going to give you a break from 340 down to 37. So there's a significant energy drop from 1s orbital electron ionization energy to 2s ionization energy. And there's great reason for that. As we learn more about Coulombic attraction and the way those values are calculated, this will make more and more sense. So we see 1s2, 2s2, 2p6. Keep in mind, as orbitals fill, they fill completely and move on to the next available electron position. 1s2, 2s2, 2p6, 3s2, 3p6, 4s. And since that 4s is half the height of a 3s, we would imagine that there's 4s1, and that would be potassium. So that's the last slide of this slideshow. I do want to show you the link that's given at the very end and that we looked at in class. And we'll pull that up now. So there that is. And what this allows us to do is click through some of the representative elements, photoelectron spectra, to investigate the various ionization energies of electrons of those atoms. And I think the most valuable thing here is to really look at what anomalies we can find. And this is one of the hottest ones in the College Board. College Board loves this one. We look at as we go from boron across to nitrogen, we notice the energies are increasing. Energies increase from boron to carbon. From carbon to nitrogen, they increase again. But when we get to oxygen, we notice that the S peaks move on and continue on increasing. But the P peak, the 2sp peak, or sorry, the 2p peak, went from 1.4 to 1.31. And just at face value, we must say that, well, adding the additional proton and additional electron did not result in a higher ionization energy. It resulted in a lower ionization energy. And because the only thing different between nitrogen and oxygen is one proton in the nucleus and one electron in the valence shell, we have to surmise that the added fourth electron contributed more to the attraction, or in this case repulsion, than the proton did. And if you think about it critically, you'll keep in mind that in the 2p subshell we have 3 orbitals. And with nitrogen, they're all singly held. That's a single same spin electron in each of the individual p orbitals. The 3 different planes, x, y, and z, each have 1 electron of the same spin. And when you add a fourth electron to create oxygen, you make an oppositely spinning electron occupy the same orbital as another electron, and that collective additional repulsion overcomes the additional attraction of having another proton in the nucleus. So we will discuss that more and more in class as we move through the unit, but hopefully that makes sense. But you are free to connect to that link and play through these values and see if what you see is what you would expect to see. And of course, as you have questions and come up with questions, please come to class with them, and I would love to talk to you about these interesting graphical findings. We'll see you in class.